Hello, I'm Bernie Zeigler, and this is a presentation based on a talk I gave recently to the System of Systems Engineering Conference in San Antonio in May 2015. It's about how modeling and simulation can help to engineer systems of systems, make them more self-improving. What are the barriers and prospects to doing so? The main question to be addressed can be formulated this way. We'll refer to systems such as healthcare system and other systems that are technology systems developed over time that are needed in reform or refashioned to meet new objectives or new conditions. We'll call those system of systems, and the component systems they're made of are called component systems. And typically the system itself is not anywhere near optimal performance for a given objective or a new objective that we're interested in. For example, healthcare is not meeting the objective of providing good health care at low cost. And so we're trying to improve it, but that's complex because it's composed of many systems. And the problem is not that the individual component systems are incapable. For example, hospitals and doctors and nurses and lab testers and so on. These are not incapable. They're very capable of what they're doing, but the organization of these component systems is lacking to make the system itself function as we'd like it to do. The problem is typically the system of systems are distributed geographically with very difficult centralization, very difficult to enforce. So we have to be smarter than trying to impose top-down control. And there are some characterizations of systems by Mayer and Boardman that go into the details of what these systems typically look like. So the system of systems engineering problem is, as formulating it here, is to design and implement a coordination mechanism that can provide the organization or help to establish the organization needed to improve the performance of the overall system toward the given objective that we're now interested in achieving. And the question is then, how can modeling and simulation help in dealing with this system of systems engineering problem? We're going to discuss two instances of system systems, ballistic missile defense and healthcare. They may seem quite unrelated, but they have certain characteristics that are shared in common. And the ballistic missile defense lets us see some of the problems and how modeling and simulation can help in a more clear manner, and then we go on to the harder problem of healthcare and how the same kinds of techniques might be helpful there. The problem in ballistic missile defense is that the component systems are each owned by separate independent contractors, and while they have individual models well developed for their particular subsystems or component systems, there's very little shared concept or modeling to guide how the overall system works together, these components work together. So in particular, it's hard to test the combined system, and in particular its command and control component in new situations like multi-missile threats, such as raid situations. On the healthcare, similar problem at the system level, but more apparent in that healthcare has been called chaotic and disorganized. The U.S. system is the most expensive in the world, but doesn't deliver the most benefits. And it's been called in need of a team sport approach. That is consistent. The players are not playing together as a team. They are each individually maximizing their own utility, and there's very little to force them to collaborate to create the best overall result. Obamacare, the Affordable Care Act, sets the stage for reform by changing the incentives, but component systems are just starting to adjust to these, and national scale coordination mechanisms are needed to help do that, make that coordination more rapid and foster it better. So modeling and simulation can help system engineers develop models of the overall system and the component systems that support design and testing of coordination mechanisms. But social barriers and other conditions, as mentioned earlier, such as geographical separation and very difficult to enforce centralization, will make the coordination mechanism hard to work. So second criteria desirable for modeling simulation is to enable component systems and coordination mechanisms to improve over time. That would mean setting up the right architecture of the support system or the support layer of integration and information technology to allow these conditions for learning, self-improvement to occur. So we'll talk about that, and we'll talk about how integrated development environments can help build and test such models, and as well as design, test, and implement these coordination and learning mechanisms. A quick background, the discrete event system specification is a formalism for modeling and simulation. It formalizes what a model is and what it must contain, what it doesn't contain. It has got good features for representation of discrete event systems in general, and more than that, a wide variety of systems can be represented well in this formalism. And it's got some good guarantees for execution, that dev's models can be executed correctly with associated dev's simulators that are based on the formalism. They understand the formalism and how to simulate models expressed in it. and the closure under coupling principle guarantees that the correctness in composing models together, which might be re-engineered, which might be changed in order to meet the new kinds of criteria for the new objectives. They might have to have models being changed, and DEVS allows the changed models to also be coupled correctly and in a hierarchical composition. DEVS models can be simulated in different execution platforms with the same basic simulator, but expressed in different ways, such as on a desktop or on a high-performance platform, such as a multi-core processor. And typically, models can be simulated as fast as possible without any additional distributed simulation or parallel simulation help. The basic DEVS simulation protocol allows them to be simulated as fast as any other more complex mechanism can do. So a model integrated development environment has design goals to allow development of composable and extensible models in simulation, align the stakeholder and user development processes, and accommodate diverse intended uses. It's based on the modeling and simulation framework where in model-based system engineering terms, it's a logical architecture design pattern for all of modeling and simulation, and it breaks down the problem into three basic entities, or four basic entities. The model, the real system or source system, from which data is being obtained and which you want to predict its course, its behavior. The experimental frame that represents the intended conditions under which the model will be experimented with, and the user's intended uses, and the model and the simulator. These three entities are related in a proper modeling and simulation study by two relations, the modeling relation and the simulator relation. The simulation is separated from the model so that changes in the model don't impact the simulation, and the experimental conditions are separated from the model so that models can be tested in different experimental frames that they might be applicable to. And the concept also supports abstraction or valid simplification of models within their application to experimental frames representing intended uses. And this is the MS4 MNS integrated development environment, that graphic illustrating the kinds of user interfaces that one would see. Underlying the architecture of the IDE is the system entity structure. It enables a model repository of reusable components and enables purpose-driven instantiation to fulfill stakeholders' intended uses. The model abstractions, different model simplifications are included in the representation in the system entity structure ontology. There's a formal axiomatic description of the SES. The basic concept is an aspect which represents decomposition or then a recomposition of a system in terms of its components, specialization, which allows substitutions of alternatives for components, and multi-aspects, which represent aspects, but for which there are many possible instances that may interact together. So, for example, in a multi-missile situation, all of the missiles would be entities, each of which would have decompositions and so on, but acting together would be represented by a multi-aspect. Pruning cuts off structure in an SES that is not needed to meet a particular objective, and the result of pruning is a particular member of a family of possible architectures. In the basic workflow, a modeler creates, the main modelers create a SES and model base and experimental frames, while users use these basic building blocks by pruning the system entity structure to achieve their particular intended use. And once pruning is done, the model can be generated automatically in a transformation that seeks the models in the model base and sews them together hierarchically to create an executable model. This concept is intended to integrate with an organization's system engineering workflows and tools. So it is to be used within the context of other system engineering tools. The concept we're talking about here is a modeling simulation-based system coordination development methodology. So the idea is that we can represent a system of systems in terms of its component systems, and typically these have to be abstracted to make simulation models. On those on the basis of these models, we can add coordination, and we'll talk about coordination mechanisms based on the DEV's pathways, and test these coordination mechanisms and decide on which coordination mechanisms work best for our particular purposes, and then implement these mechanisms in the real system using the fact that the DEV's models, the coordination models, can transfer from the modeling description into actual real-time operation in a very straightforward manner that doesn't require changing of code, but more additional code that can be done automatically. So we have an environment that can take DEV's models that have been developed, in particular pathway models, and allow them to execute in web and cloud-based environments. This mapping is automatic, and therefore converts whatever was supposed to happen in the simulated world into actual controls and interactions with users in a web environment. In our instance for the ballistic missile defense system, the system entity structure represents a family of systems of ballistic missile defense. Particular model configurations are specified by selecting alternatives from choices, the component system specializations. The experimental frame or frames represent the intended use of the models. In this case, measuring performance of the BMDS in an end-to-end manner. The experimental frame computes the system of system embedded performance assessments of alternative system components. So the user has been selecting alternatives, and these are being tested and measured both from their own performance criteria, but also how they correlate with the overall system performance. And based on the components' participation in the system, components' credit can be assigned as to how well that system contributed to the overall performance. So that alternative contributed so that over extended operation, extended simulation, the best alternatives will emerge. Stochastic Monte Carlo runs enable statistically significant estimation of these performance measures and deriving of best compositions, for example, within multi-missile threat environments. The Markov-based simplifications that we'll show will demonstrate how, for particular intended uses, models can run much faster than the more complex models from which they're derived. For example, here is a SysML activity diagram of BMDS, and there's a target, a SIBRS, TPY2, Aegis Spy, Aegis SM3, components that are typically involved in a command and control component. And each component has a lifeline and interactions among these components are indicated by arrows occurring at different points in the lifetime. So in this case, we have a system entity structure that briefly illustrated here. This has the components, and here are illustrated alternative, low resolution, high resolution sensors, and low capability and high capability tracking. So there are these two components that as examples have alternatives that can be selected and combined and tried within the context of the overall system. So once having made a choice by pruning, this kind of model is generated with the components and their coupling, and simulations can be run. The alternatives will be plugged in, and a simulation run of end-to-end operations from the arrival of a target through its detection and tracking and interception will be generated. This kind of behavior will be generated by the simulation model, and performance messages, performance indices will be developed and computed based on the experimental frame monitoring the message exchange among the components and determining the level of success in detecting and intercepting the target. And these performance assessments and credits of the relative performance levels of the alternatives will be output and saved so that successive simulation runs will develop overall averages for how well alternatives do within the context of the simulation. In a multi-missile situation, you have the same kind of story, except that many instances of that single system can be run at the same time, and each of which can be also pruned, and so different prunings can be running at the same time, and each gathering, each component being watched and compared to generate overall success measures for the components and the system. There's also a credit aggregator that compiles the credits assigned to component alternatives over multiple alternative compositions. For example, here it's shown as 3 with different prunings, and over time we get a representation of how well components alternatives are doing. So typically here, as an example, the high resolution SIBRs and high capacity tracking will emerge as the best in over many runs, but that would verify what we know as having built this example as just an example. And the credit aggregator outputs the best alternatives, ones that get the highest credit compared to their competitors. Ballot simplifications are useful in that these kind of runs can take a lot of time to execute, and there's a value to simplification, which will allow for some performance, some intended uses, to have much faster running. The dev's environment now supports continuous time Markov models that can represent individual actors in a system of systems, such as agents, in a very expressive way, and allow probabilistic description, probabilistic choices of alternative decisions and times for state changes, and we can develop queuing-like performance metrics and other time-based metrics, and allow this kind of correlation of behavior of components with overall outcomes. And both transient steady state analyses can be done. But for certain indices, these continuous time Markov models can be simplified automatically by pressing a button to what we call Markov finite chain matrix models, which yield probabilities for the continuous time models in the steady state. But they cannot represent individual actors as the original models can. They can only represent, in effect, cohorts of individuals, different individuals with the same kinds of the same characteristics. But they can yield both steady state and transient time averages for these kinds of cohorts. So instead of models that you watch individuals flowing through, you in effect predict using the simplifications. You predict what cohorts of individuals do, both in transient and in the long run. So the example for in the BMDS is that we have in the boost phase, for example, the target, the SIBRs, and the command and control that are represented in a simplified way so that they exchange rates of message or state changes rather than individual messages. So the rate at which targets send out their booster plume would be computed by a Markov simplification, while in the original, the actual message representing that plume is generated by an individual target. Here's an example of the SIBRs represented as a continuous time Markov model, and then a simplification to a matrix Markov chain type model. The activity diagram I showed before, and supplemented by a spreadsheet in which the state changes are given, and their duration and their recurrence and probability of occurrence are given. These are converted into actual probabilities for the state transitions, corresponding state transitions in the CTM model in the DEPS environment. The dotted lines indicate these probability assignments, and other lines are typical DEPS models. For example, inputs and outputs that allow this component to be coupled together with others, and that illustrates that Markov modeling is incorporated in an integral fashion within the DEVS environment, so that you get the advantage of representing models quickly and easily with Markov in a continuous time manner, which is also as efficient as you can get for because it uses discrete event simulation underneath it. But also you can then couple these components together, for example, to create the BMDS. And then by pressing a button, you automatically can generate a simplified Markov model that we talked about that represents the same kinds of inputs and outputs, but in terms of rates rather than messages. Now going on to healthcare, we can visualize the current state of U.S. healthcare as multiple or myriads of interventions, treatments, various services that are provided, medicines, prescriptions, and so on. But they're disorganized in the sense that for a single condition, there's no sort of generally recognized sequence in which these are all strung together. Although for particular kinds of diseases and maladies, let's say, there are such, such sequences or compositions of these services. Typically, there's nothing overall. And to constitute an end-to-end treatment for a medical condition, that means that the services have to be strung together in a fairly chaotic and haphazard manner, which is both time-consuming and costly, and may result in errors and sometimes fatal or costly errors. So it's more rational to have what can be called a care delivery value chain for each kind of condition, in which the services are aligned and in which they're identified and form a low-cost, high-quality care delivery value chain. This would result in faster, better treatment at lower cost. The concept of pathways is developed to implement such care delivery value chains. We are applying this concept in a current project with Prince George's County, which is called Patient-Centered Coordination of Care Services. And it's a layered health information technology architecture. The problem addressed is that you have these multiple services, social services and care, medical services, other services, behavioral health, and so on. Some of which apply to a particular patient and need to be coordinated for that patient. Currently, the patient is more or less on their own to manage that, how to deal with those the instructions through from the doctor, let's say, that has prescribed different things to do, medicines to get. But there's currently no support, very little support for that patient to put these services together in this care delivery value chain for that particular condition. This concept of patient-centered home brings together a team of nurses, doctors, pharmacists, behavioral health providers, and so on for a given condition, so that the patient's care can be coordinated and tracked and monitored. And that is what the pathways concept does. And it's built on a layered framework in which there's a network of communication allowing these various services to be tapped into, and a health information exchange layer that allows the patient's records to be found and updated no matter where they are, whether at home or hospital or different locations. And on top of that, the pathways coordination of different services applicable to particular conditions. So the problem is that there are myriad independent and semi-autonomous service providers, and they require coordination to properly care for a patient. The pathways concept provides a layer implementing coordination, monitoring, tracking, and measurement. These data are gathered through monitoring, tracking, measurement, and so on. They can be aggregated and credit assigned to different versions of the support services, and this can then support self-improvement, as indicated with the BMDS example, that different alternatives can be tested in the context here of actual operation. And because there's so many places in which all this can be going on, different patient homes and different locations and so on, we can have a more efficient testing, more because we can get many trials going on at the same time. So this provides necessary, sufficient architectural features or conditions for self-improvement of system of systems. Pathways provide the possibility to coordinate these processes, and this slide goes into more detail about how the pathways are implemented as DEVS models, and they have certain properties that always end after a certain time with either success, that a particular pathway was successfully completed, or failure, or incomplete because the time has elapsed for this pathway or sequence of steps to be implemented or achieved. The importance is that the pathways always report their results in a finite time, and that the monitor or the supervisor can take action and get warnings and alerts and respond in time, but also that data collected is always resolved into one of these three outcomes. These pathways can operate in series or parallel or combinations, and that means that there can be multiple pathways taking care of multiple sub-problems, sub-goals within a main pathway or main goal to be achieved. And the information gathered in the pathways, in a pathway and pathways can be combined to produce ratings of components as we indicated. And this can allow, as we say, a self-improving system in the sense that there's information collected, and better components can be identified, and better strategies or protocols can be instituted to become the actual selection or best practices of the system. So in summary, how can modeling and simulation help system engineering in the development of coordination for systems? It can help build and test models of the system as well as the components to design, test, and implement coordination and learning mechanisms. It can help engineers to design and test coordination mechanisms, allow them to, or enable them to self-improve over time, and it can provide the basis for necessary and sufficient conditions or architectural features for such learning. We've shown that the example of the MTS, the environment supports end-to-end system models to test the interaction and coordination of the component systems in multi-missile threat environments. And the pathways provides a layer, important layer, a critical layer for health information technology, which allows more patient-centered coordination of care. So allows providing or introducing the care delivery value chains to be implemented and instituted, and in that way can improve both the delivery of care and reduce the cost while doing that. Thank you for your attention. This is a list of publications that provide some background that can be augment the presentation discussed here.